So thank you very much, Claudia, for the nice introduction. And I'm happy to be here. So I've been in Germany in the past and in Berlin a few times, but I don't come very often. Really, it's a pleasure. And let me, so this is, as Claudia was saying, I have recently left the University of Missouri after many years. I've taken this temporary position at the National University of Singapore. And here, in your honor, I put a picture of the most iconic building of Singapore, the Marina Bay Science Tower.
It's a pool up there.
There is an infinity pool over there. Exactly. And this somewhat less impressive building is the place where the Institute for Functional Intelligent Materials is. Okay, so I have been working with a number of mostly postdocs actually there, and I would really like to tell you what I have been up to. Okay, so you will notice that I don't have a whole lot of results to present, but I have several ideas, and I think I'll be able to describe to you, the ideas we are pursuing. These groups, many of these people are software engineers. For example, Min Lin here is the group leader of the AI lab at SEAS. This is an industrial company. Okay, so these first two guys are definitely software engineers, and I'm enjoying very much the collaboration. I'm not a computational person myself, but I think I'm learning a lot. Stephen Dale is my postdoc. There are two more, one of them working on completely different things. But these two guys are the famous ones, okay? In particular, Kostya Novoselov is the director of the institute, and I'm sure many of you know him from after he won the Nobel Prize for the discovery of graphene, and Antonio Castroneto is the co-director of this institute. Okay, so let me first of all, so I will say first of all things that are quite well known and a little bit boring perhaps, but I will repeat them just so that everybody feels at ease. And in this institute probably better than I what the problem of material science is, in its very general term, is a problem to determine, a ground state electronics wave function for this type of Hamiltonian, kinetic energy plus electron-electron interaction plus an external potential, and the real, one of the key insights of the density functional theory from the very beginning was to recognize that there is a certain universality to this problem, meaning that a large part of the Hamiltonian that I wrote is really completely independent of the material, right? The material characteristic enter only in that external potential term, which is characterized by the electron-ion interaction, which is ultimately by the structure of the, which atoms and in what position they are. And interestingly, that electron-ion potential couples to the electron density operator, okay, at least in the simplest non-relativistic case. Hence you can immediately see that the density stands out as a special quantity, is the quantity through which the material or the electrons in the material talk to their own environment. Okay, so that I think led Oemer and Kohn to make this attempt to formulate mechanics in terms of the density. So essentially to replace the very difficult problem of minimizing the energy with respect to the wave function by the somewhat simpler problem minimizing the energy with respect to the density, okay? And of course, this was allowed by the fact that they could prove that the density uniquely or quasi-uniquely determines the wave function and so on. But we will not go into those details. Okay, so you know, they exploit the universality of you know, the largest part of the Hamiltonian by introducing this so-called universal functional, the famous f of n, okay, which can be formally defined as the minimum over all the antisymmetric wave functions that yield a certain density, called n, the minimum of the expectation value of kinetic plus potential. So only the universal part of the Hamiltonian enters there. So if you could calculate, okay, this functional, which sometimes is called the holy grail of density functional theory, you would really be in business, because this is the same for all materials, okay? So you don't have to recalculate it every time. So no matter what you study, it's always the same f, and only the external potential changes, only, you know, in inverted commas. Okay, so now another crucial step was the partitioning of the universal functional into a kinetic, or more precisely non-interacting kinetic energy part, about which I have more to say later, okay? And the Hartree potential, which is a classical electrostatic energy, okay? And a remainder exchange correlation functional, which became soon the object of many approximation. It was butchered in many ways and so on. Anyway, now, the final point to make is that all this actually became so wildly successful, perhaps beyond the expectations of the inventors and many other people, because a way was found to effectively restrict the search over densities, which by itself is a rather uncontrolled search, to densities which make physical sense. So in particular, densities that are consistent with Pauli exclusions principle. And such densities should be, or not necessarily, but the simplest way to represent them is through as sums of densities of one electron orbitals, okay? So that the Pauli exclusion principle is somehow hardwired into the calculation. Of course, the moment you pass from the density to the orbitals, well, you know, you are multiplying by n the number of your unknowns, where n is the number of electrons. So the scaling becomes somewhat worse. You know, it's now these days believed to be n cubed, right? But you can show, and it was done very early on, that the problem of minimizing the energy with respect to the density becomes equivalent to solving these self-consistent Constraint equations for the orbitals psi I, which determine the density, but also the self-consistent potential, for which by now there are hundreds, literally, of different approximations. Okay, very good. So, why is so? I must say, as a historical note, since I came here for an interview about DFT, I had prepared a few notes here for myself. That you know, I remember distinctly that there was great skepticism initially about density functional theory. You know, in particular, it was skepticism from chemists who simply did not believe that the thing as complicated as you know, the wave function, you know, could be somehow described as something as simple as the density. But I think there was even worse than skepticism. It was disdain from particularly the highbrow theoretical physicists who thought that this was just a simple-minded theory and so. But actually, after a few years, you know, the Consham DFT really won the day, became one of the most successful theories ever, for a variety of reasons. Largely, its simplicity. It's in fact simpler than the Hartree-Fock equations, but it includes electronic correlations. Simpler because the potential is local in density functional theory as opposed to the non-local Fock exchange. The complexity, well, n cube is not great, but it is great if you compare it to the exponential wall that we face in the many-body problem, if you really go for the wave function, okay? And most importantly, it precisely matches the capability of this generation of computers. You see, perhaps one day when we have a quantum computer, we'll be able to start seriously doing the many-body problem. But for the time being, with the computers we have nowadays, this is really they are the right tool for the right problem. And also a psychological reason that I want to emphasize is that it basically transformed what had been until then a kind of a very empirical type of research, you know, going for cooking recipes like the X-alpha exchange. All of a sudden, that was transformed into something much more noble, much more high-minded, you know, so the quest for the exact function of density functional theory. So I think that motivated many scientists to join the quest, okay? All right, so on the other hand, having said all this, it's also true that the scheme has many limitations. I observe that nowadays people, particularly people in artificial intelligence, they tend to look up to density functional theory as a kind of oracle that is supposed to tell them the truth, you know, about the material. Now, to me, it seems clear that nothing could be farther from the truth in general, okay? So it relies on uncontrolled approximations. There are serious and systematic errors, particularly for ground states that are, you know, quasi-degenerates, strongly correlated. And here is a list of the best documented systematic errors, starting with self-interaction, which probably by now is more or less under control. Derivative discontinuities and closely related electronization error, which I guess are not yet completely solved. And then these other you know, questions having to do with the symmetry, contamination, static correlations, and so on. So we will not have a good solution, really, of the material science problem until, you know, at least within the framework of DFT, and until all these difficulties are resolved. Okay, so now what I would like to say is tell you a little bit what we are doing in this direction. Is, you know, very modest effort. So I would say that there are at least two ways in which we can you know, put the capabilities of software engineers, such as the ones at the C Artificial Intelligence Lab. There are several ways in which we can use their talents to advance, okay, this field of density functional theory. And so one is to speed up and also perhaps make more reliable, you know, the implementation of con-sham DFT calculations based on existing functionals. So this part of the project does not deal with improving the functional, but to improve maybe the precision, the efficiency, and so of the algorithms, okay? And the second possibility, which is more fundamental, is to use these deep learning techniques to actually improve our knowledge of the functional. So ultimately to produce better functionals than what we have now. Okay, so the project, what I will describe to you is a little bit of the first and a little bit of the second. Okay, so let's begin with the first thing. Okay, so so the idea here is the first. So I think you will probably agree that the most commonly employed mechanism framework for implementing density functional theory is the con-sham, the iterative solution of the con-sham equations, okay? Which I would say by and large works, but also it has some limitation. In particular, the convergence is not always guaranteed. You know, sometimes the equations get trapped in a loop that keeps oscillating back and forth without reaching convergence, okay? So here we decide, because the essence, you know, of neural networks is essentially, you know, the ability to solve optimization, minimization problems very efficiently. So every problem ultimately should be really mapped as far as possible into a direct optimization problem. So there is an approach to density functional theory which goes back to a 1997 paper by Marzari, Vanderbilt, and Payne. Some people called it variational DFT. And the idea is that instead of solving self-consistently the Kohn-Sham equation, why not just try to directly minimize the free energy, not just the energy, but the free energy. I'll tell you later why we need the free energy, not just the energy, okay? As a functional of what? Of single particle orbital psi I. Those are needed to represent the density, okay? As I said, in a way consistent with Pauli principle. But also, not only the orbital, but also an occupation matrix, okay? Because there are, in fact, particularly in metallic system, extended systems, there are often ambiguities in which states you should, which of these orbitals you should occupy, okay? Just like even when you fill the periodic table, you know, of elements, right? At some point, you run into ambiguity whether you should put the next electron in the, let's say, in the 3D or in the 4S state, right? So there are this kind of ambiguity. So this means that the occupation of the orbitals should be determined on equal footing as the orbitals themselves. And this is the fundamental reason why we need to go beyond just the energy, but also include a small entropic term. You see that last term here, probably I should say more about this line. Okay, but the last term there is a fictitious temperature times an entropy, which is a functional of the occupation of the distribution function. We don't include that because we care about the temperature. In fact, we don't care at all about the temperature, but it helps us to regularize this problem of the occupation. So in effect, what we are doing is an ensemble density functional theory in which the occupations become smooth functions, okay? But anyway, so the first part of this free energy functional should be clear by now. So the first term is the non-interacting kinetic energy, given in terms of orbitals and occupation number. The density itself is given in terms of orbitals and occupation function, okay? And then the rest of the energy is entirely expressed in terms of the density according to the time-honored precepts of density functional theory, and that is the external potential. So we basically now have a complex optimization problem in which the thing to be, the variables of the optimization are the psi i's and the gamma ij's, okay? But of course, there are constraints on those, and that's one of the main reasons why Kohn-Sham is usually the method of choice, because one of the nice features of the Kohn-Sham equations is that it automatically guarantees, by virtue of being a Hermitian eigenvalue problem, it automatically guarantees that the orbitals will come out orthogonal to each other. That's one of the requirements. Okay, so you don't have to worry about that. But if you do minimization directly like this, then you know, you have to take into account that otherwise you might end up solving a problem of bosons instead of solving a problem of fermions, right? If you don't ensure the orthogonality of these guys. Okay, so that is important. Also for the occupation matrix, it's very, there is a physical constraint that the eigenvalue of that matrix should all be between 0 and 1. Again, is a consequence of Pauli's exclusion principle, okay, essentially. All right, so this, by the way, is the most physical choice of the entropy functional expressed in terms of the eigenvalues of that occupation number, but it's not by no means the only possible choice, because, as I said, we don't really care about the physical temperature. We care about the minimization. And so there are lots of schemes by now called smearing schemes, which, by the way, I'm sure that some of you know better than I know how those things are applied in practical calculation. Okay, now let me try to describe briefly the work that we have been doing since I have been there at NUS. Okay, so essentially we want to parameterize the constraints that I mentioned so that they are hardwired in the calculation. We don't have to worry about satisfying those constraints anymore, okay? So how is this done? So first of all, the orbital psi I are expanded on a plane wave basis. But you will have noticed by now that I am focusing on periodic crystalline systems here, okay? So I'm not dealing with molecules in this work. So we are using, up to this point, actually, we are still doing all electrons. You know, I'm sure at some point we'll have to abandon that and start doing pseudo-potentials. But for the time being, we are expanding our orbitals on a basis of plane waves, okay? And here is the clever trick that the guy at C came up with to enforce the confidence, a trick called QR decomposition. Basically, this QR algorithm is a general algorithm that works on any rectangular matrix in general. So you can start, for example, from a generic rectangular matrix, which has the same dimensions as that matrix of coefficients up there. Okay, so what are the dimensions? One dimension is G, the number of elements in the plane wave basis, and the other dimension is I, which is the number of potentially occupied bands. Okay, so you start from a generic G times I rectangular matrix, and you can write, following this algorithm, as a product of a unitary G times I matrix times an upper triangular matrix. And don't ask me why the second matrix has to be upper triangular, because I've never understood it. That part is thrown away, okay? And in my opinion, one could save time by not insisting on that part being upper triangular, but they tell me that this QR algorithm is particularly stable, it's differentiable. All these are things practically important, so they assure me that it's better to do it like this, okay? But the point is that this R part will be thrown away, and what will be left behind is a rectangular matrix with the same shape, as the original random one, but with orthogonal columns. So you might think of this as a kind of Gram-Schmidt orthogonalization, but done in a different way. Yes. So you start from a generic X, and the matrix or the coefficient is the Q part of the QR decomposition of X. Okay, so X becomes your variable, the thing that has to be learned by the optimization algorithm, okay? And so the constraints are now automatically satisfied because these things are orthogonal to each other. The columns of the matrix are orthogonal. So, yeah, so, okay, so having said that, right, so we have now these two variables, the X and the Y matrices, and the minimization is done by steepest descent, okay? Steepest gradient descent, okay, with respect to these G times I matrices and IK times NK. Now, K is the number of K points in the grid, okay? N is the number of electrons per unit cell. So everything is nicely defined here. The constraints are all now hardwired, and the calculation is differentiable with respect to input parameters. So one of the things that we hope to be able to do, for example, is differentiate the energies with respect to the nuclear positions, get forces, very straightforwardly, and so on. Now, we have one published paper on this. So both papers have been submitted to this important conference on International Conference on Learning Representations. It's an important AI conference, okay? And this one has been published. This one, I'm afraid we will have to look for a venue, to publish it. But anyway, so the first one was actually a molecular code, and the second one is, closely similar, but not quite. It's for solids. Okay. So that's basically where we are now. So I'd like to be able to tell you now that we have fantastic results, that we get convergence, in 1/100th of the time that takes quantum express, but it is not so. It is still quite slow. There are lots of details to be ironed out. Generally speaking, we can calculate band structures of metals, semiconductors, and insulator. They look nice to the eye, but we are still a little bit into a benchmarking process. An attractive feature of this is that it is all written in JAX, and they tell me that this is very good because this can be also, this software will be implementable on the GPUs eventually, and it will go very, very fast and so on, but we'll see, okay? Because, so this is the project that directly involves the artificial intelligence guys at sea. Now, I would like to tell you something about, a project is very dear to my heart, okay? Yeah, which potentially could be very important, I guess, for density functional theory. It's certainly not the first time that somebody has tried to construct the exact non-interacting kinetic energy function. So there have been many attempts. Essentially, this is the problem of the inversion of the Kohn-Sham equation. Okay, so the idea is, given a density, find the potential that produces that density in a non-interacting system, that is, the Kohn-Sham system, right? So it's a classic problem in the field. Many people, going back to Barents and Wei-Tao Yang, and so have approached. So, I like to say that along the road you see the bones of many people who died in the process, in the attempting to solve this problem. But let me show you why I started thinking along these lines. Okay, it was all inspired by what the AI people were doing in the previous slides. Okay, so the problem that we want to solve is again an optimization problem, but now it has a completely different constraint. Okay, so the problem of calculating this Ts of the density is the problem of finding the minimum of the kinetic energy operator, expectation value, with respect to all wave, orbitals, orthogonal orbitals that yield the prescribed density. So there is an additional constraint that was not there before, right? Before we were minimizing. So in the previous calculation, the density that came out was the actual ground state density of the system, right? And whatever it has to be. Now here, somebody, right? So Pasquale tells me, okay, I want, this density, I like it. Tell me what is the kinetic energy associated with that density, okay? And I have basically to solve this optimization problem, okay? So with this extra constraint that the psi yield n. Okay, so now if I present it this way, which is not the way it was originally thought of, but anyway, is closely related. So you see immediately that this is in a way, very similar to the optimization problem we solved before, except for this additional constraint. So this gives us the idea that maybe those techniques of QR decomposition, that I illustrated before, they could be used to solve this problem. Okay, which is a different one. Now, I must say that if one could really solve this problem efficiently, meaning that, I can give you in a matter of a fraction of a second, I can give you the answer to your question, it would really be very good for density, because it would open the doors to a completely orbital-free density functional theory, okay, in which you really work only with the density, okay? So the orbitals disappear completely. I think that would be a significant achievement, if we can do that. Okay, very good. So now, okay, so that is the statement of the problem. So now the idea is it is an idea that actually goes back to many years ago, really, to papers by Harriman, and then later it was taken up by Francois Gigi, in the 90s, okay? But we are trying to do the following thing, okay? So we want to sort of, in a way, to build the constraint into this search, okay? So to do this, we introduce a new basis of functions which look like plane waves, but they're not really plane waves. Okay, so they're deformed plane waves. Okay, they were introduced by this guy Harriman back in ages ago. Okay, and they're called sometimes equidensity orbitals. Okay, so the characteristic of these wave functions is that, first of all, you see that all these orbitals, they have the same density n of x, whatever Pasquale suggested is built in there, because this factor is just a phase factor, right? So modulus square of that is 1. So the density of all these orbitals is n of x. However, because this psi of x is some function, I'll come back to this in a moment, then these orbitals, it turns out that with the proper choice of psi of x, they are orthogonal to each other, in fact, orthonormal, okay? And they form a complete set of orthogonal wave functions, all having the same density. Okay, that's why we call them equidensity. It's a complete set of orbitals, or you could call them distorted plane waves because of this, okay, which all produce the same density, but they also form a complete set. Okay, so now this orthogonality and completeness will not happen generically for any choice of psi, but it will happen if psi is chosen judiciously. Okay, and what it means is that this psi is a map of the unit cell into itself, which transforms a uniform density n bar, given by the number of electrons per unit cell over the volume of the unit cell, into the actual density that we are trying to describe, the density for which we want to calculate the function. Okay? So there is a map that invertible, okay, that goes from uniform density to any density you want. In fact, it can be generalized. You can show that there is a map that transforms any density into any other density, okay? And that should be potentially important for density functional theory, to be able to do this transformation. But here, we go from uniform to the target density, and the choice of psi is determined by the solution of this so-called Jacobian problem, which says that the Jacobian determinant of the map, psi, must be essentially equal to the ratio of the final density to the initial density, okay? So the G vectors here are quantized in the usual Born-van Karman way, so that the periodic boundary conditions are satisfied, okay? So now I wish I could tell you that this, the solution to this problem is unique. Unfortunately, it is not, okay? It is, however, unique in one dimension, okay? And I will show you immediately. In one dimension, there is a very trivial solution, actually, which is that, okay? And this was noted long, long ago, So psi of x in one dimension is simply the integral of the density, up to point x. So, for example, if your density in the unit cell looks like this, then the map psi of x will look like that blue line. And notice that it's invertible perfectly. So it's monotonically increasing, so it's invertible. And so there is absolutely no ambiguity. When you go to 2 and 3 dimensions, there is a lot of ambiguity because you can do lots of shear deformations which do not change the density, but of course change everything else, okay? So you have to include additional criteria to optimize. And this is something that the AI people like, because it gives them an opportunity to optimize the deformation, make it, find the best possible deformation to get the best possible, the lowest possible energy, okay? But anyway, without going into that now, so this is what we started doing. This is my postdoc who has been now struggling for a while with this calculation. So basically, we expand our block wave functions not in a basis of plane waves, but in a basis of these distorted plane waves, okay, equidensity orbitals. Okay, those are the phi k plus g, which I defined in the previous slide. And then, again, so we have the same rectangular matrix that defines our orbitals, okay? And we can, again, make sure that it's orthogonal by the QR decomposition. So all this remains the same, okay? So this is basically the condition of orthogonality. We can also construct the density matrix in terms of these coefficients. This is the one particle density matrix, okay? So you see C dagger C is an identity, but C dagger is the density matrix here. And then, having done this, and here comes the interesting and new thing, we have to make sure that our state has the prescribed density, right? And it is not guaranteed, because even though the basis orbitals are all of the same density, this does not yet guarantee that any superposition of those orbitals will have the prescribed density, okay? Because there are unfortunately interference terms between things. However, and here is where the advantage of using equidensity orbitals shows up, we can show that the constraint of prescribed density takes a simple and universal form in this basis, okay? First, let me tell you what the form is. The form is that all the subtraces of the density matrix are zero. By subtraces, I mean the sums of the elements along these lines parallel to the diagonal. Okay? All the subtraces must be zero, while the principal trace is equal to the number of particles, as usual. Okay? So with this simple requirement, which, as you see, does not depend explicitly on which density has been given to me, okay? It's a universal constraint, okay? So I am sure, if I satisfy that constraint, I am sure that the density will come out right. And this is because the density has been inbuilt into the basis, okay, through this choice of the equidensity orbitals, okay? So that's basically the interesting thing, and that now at this point allows us to do the calculation. So this is the explicit form of kinetic energy. There's only kinetic energy now, okay, in terms of that matrix C that described. And then there is a penalty term which enforces the constraint on the subtraces. The purpose of that penalty term is to try to suppress to make sure that those subtraces are all zero, as they should be. Now, there might be better ways of doing this. Okay, so it's not, in a way, the constant is not really completely parameterized into the calculation, because we still need to enforce it by this penalty factor. And so if we find a way to get around this, we'll be in real business. But for the time being, we're still, this reduces the accuracy of the calculation, because you probably know, whenever you use these penalty methods, it's a delicate balance between, it's a little bit of an art, to choose that lambda factor large enough that it does its job of suppressing, the thing, but also not so large that you completely screw up the quantity that you wanted to calculate. So that is definitely a weak point at this point of the calculation. Okay, so. Okay, so anyway, with the penalty in place, we can optimize. This goes relatively fast, so 30 iterations per second, and we converge in something of the order of 200, let's say, iterations, and then and then you start getting results, So now, of course, you want to benchmark this. And so far, the calculations are not terribly satisfactory, the results, okay? I mean, this is, so for example, if you solve a so-called chronic penny model, okay? Now you can start laughing at me because I solved the chronic penny model, okay? Now, is that model there, right? It's basically a square, a sawtooth, not sawtooth, a square well potential repeated periodically. And we know what the exact energy, actually we focus on the so-called Pauli kinetic energy, okay, but that's a detail. Okay, so this is an exact number. This is what we get from the optimization This is atomic unit, so we are not doing that great yet, okay? So, you know, paradoxically, we seem to be doing better when we have a non-full band, okay? Don't quite understand why that. In this calculation, there is 7 electrons and 7 unit cells. So there is a full lowest band occupied. And yeah, so forget that. But on the other hand, if you, here in this case, you know, 7 and 9, so you can do fractional occupations without any problem here. You can consider fractionally occupied band. And in this case, it works, you know, exact result and minimization is working better, okay? So also you can see how well the constraint is satisfied, okay? So the computed density and the exact density for this particular situation, yeah. Yeah, yeah. The exact upper bound is something, is not very useful because it's a loose bound, but basically, so I can tell you first of all what it is, okay? It's the sum of the bosonic energy and the Thomas Fermi kinetic energy. Bosonic energy, I mean the von Weizsäcker potential, grad n squared, okay? So that is a rigorous upper bound, and it follows by, so if you choose as a trial wave function simply a single slated determinant of equidensity orbitals, okay? Then that gives you, so yeah, so basically you choose the smallest k vectors, equidensity orbital associated with them, and you populate only that, and then you calculate the kinetic energy. The result is von Weizsäcker plus Thomas Fermi, and that is an exact upper bound. Okay, but as you can see, is a pretty weak bound, so that there is not much here to. It just mostly is a test that we are not doing something grossly wrong. Okay, so at least we are below that exact upper bound. Now, okay, so this is a density for which we don't have an exact result. Okay, so there is out of the set, so to say, and so there is no exact results here. And but we get a number. Of course, at this point, I have no way to tell how good that is, unless I compare with some other inversion method like Wei tau and so on.